Black holes were once believed to be the most perfect traps in the universe. Once something crossed their boundary, it was gone forever. Light could not escape, matter could not escape, even time itself seemed to fall inward and never return. For decades, scientists were confident that black holes were eternal objects, silent and unchanging, sitting at the end of cosmic history. They were thought to be the final destination of matter, the place where the universe locked things away permanently. Nothing came out, nothing leaked, nothing faded. A black hole, once formed, was supposed to last forever. That certainty began to crack when one simple question was asked. What if empty space near a black hole is not truly empty? What if the universe does not allow perfect stillness, even at the edge of something as extreme as a black hole? This question led to one of the most surprising ideas in modern science, an idea that said black holes are not truly black, that they slowly lose energy, shrink, and eventually disappear. This idea is called Hawking radiation. At first, Hawking radiation sounds complicated and mathematical, but the core idea is simple. It comes from the strange behavior of empty space. According to modern physics, empty space is not nothing. Tiny particles constantly appear and disappear everywhere in the universe. Normally, these particles vanish almost instantly, leaving no trace. But near a black hole, gravity is so intense that it can disrupt this process. When particle pairs form right at the edge of a black hole, one can fall in while the other escapes. The escaping particle becomes real and carries energy away. That energy comes from the black hole itself. Slowly, over an unimaginably long time, the black hole loses mass. It fades, it evaporates. The process is incredibly weak and incredibly slow. A black hole as massive as the sun would take far longer than the age of the universe to disappear. But the message is clear. Black holes are not eternal. Even the strongest gravity cannot completely stop change. This idea changed science forever. It connected gravity with quantum physics in a way no one expected. It also raised deep questions that scientists are still trying to answer, including what happens to information that falls into a black hole. Hawking radiation reminds us that the universe is stranger than our intuition and more subtle than our assumptions. In this video, we're going to explain Hawking radiation without equations or technical language, just clear ideas and careful reasoning. By the end, you will understand how something once thought to live forever can quietly fade away, and what that tells us about the true nature of the universe. For a long time, black holes were seen as the most final objects in the universe. They were not mysterious in the poetic sense. They were mysterious in a hard, closed-door sense. Once something went in, the story was over. Scientists believed this with deep confidence, not because they lacked imagination, but because every rule of physics they trusted pointed to the same conclusion. Black holes were born from gravity, and gravity, when strong enough, seemed unbeatable. If gravity could crush a star, bend space, slow time, and trap light itself, then nothing should be able to escape its grip. This belief shaped how black holes were understood for most of the 20th century. They were not glowing objects, they were not changing objects, they were cosmic endpoints, the ultimate dead ends of nature. To understand why scientists were so sure, we need to go back to how black holes entered physics in the first place. Black holes were not discovered by looking through telescopes, they came out of equations. When Albert Einstein published his theory of general relativity, he showed that gravity is not just a force pulling objects together. It is the bending of space and time caused by mass and energy. Most of the time, this bending is gentle. Earth bends space a little. The sun bends it more, but the equations also allowed something extreme. If enough mass was squeezed into a small enough region, space and time would bend so sharply that all paths would point inward. That region would be completely cut off from the rest of the universe. At first, even Einstein did not believe such objects could exist in reality. They seemed too strange, too extreme. but later work showed that nature could indeed create them when massive stars collapsed. When a very large star runs out of fuel, it can no longer support itself against gravity. The core collapses inward, under its own weight. In some cases, nothing stops the collapse, not pressure, not nuclear reactions. The matter keeps falling inward, becoming denser and denser. Eventually, a black hole forms. At its center lies a region where density becomes unimaginably high. Surrounding that center is a boundary that defines the black hole itself. This boundary is what scientists call the event horizon. The event horizon is one of the most important ideas to understand when talking about black holes. It sounds technical, but the idea is simple. Imagine a river flowing toward a waterfall. Far upstream, you can swim against the current and escape. As you move closer to the edge, the water flows faster. At some point, the current becomes so strong that no matter how hard you swim, you cannot move back upstream. That point is the point of no return. The event horizon is like that point, but for space and time instead of water. Outside the event horizon, escape is possible. Inside it, every possible path leads deeper in. Not because something is pulling harder, but because space itself is tilted inward. This is why scientists said, "Nothing escapes a black hole." It was not a slogan. It was a logical consequence of how space and time behave near extreme gravity. Light follows the paths of space. If all paths point inward, light goes inward too. And if light cannot escape, then nothing else can either. Matter, energy, information, signals, everything is trapped once it crosses the event horizon. From the outside, the black hole appears silent and dark. It does not send messages. It does not glow. It does not reveal what is happening inside. It simply exists. Because of this, black holes were thought to be completely cold. In physics, temperature is related to motion and energy. Hot objects emit radiation. They glow or give off heat. Cold objects do not. Since black holes were believed to emit nothing at all, they were assigned a temperature of absolute zero, as cold as something can possibly be. This made sense under the old view. If nothing comes out, then no energy leaves. If no energy leaves, the black hole cannot cool or change. It must remain exactly as it is. This led to the idea that black holes were eternal. Once formed, they would last forever. They could grow by swallowing more matter or merging with other black holes, but they could never shrink. Time could pass, stars could die, galaxies could fade, but black holes would remain. In the far future of the universe, after all, stars had burned out. Black holes would be the last objects left, silent, massive, unchanging, cosmic fossils marking where matter once existed. Because of this, black holes were often described as cosmic dead ends. In science, a dead end is a place where processes stop. Nothing interesting happens beyond it. Black holes fit this idea perfectly. Matter fell in and disappeared from the observable universe. Information about what fell in was lost forever, at least from the outside perspective. The black hole itself could be described using only a few properties: mass, charge, and spin. Everything else seemed erased. It did not matter what kind of star formed the black hole or what objects later fell into it. The outside universe could never know. This idea was summarized by the phrase, "Black holes have no hair," meaning they carry no detailed information. This view was not careless or lazy. It was careful and logical. It came from combining general relativity with classical physics. According to those rules, black holes were perfectly consistent objects. They did exactly what the equations said they should do, and for many years no one seriously questioned the idea that black holes were eternal. But there was a quiet tension beneath this confidence. Another branch of physics, quantum mechanics, was telling a very different story about reality. Quantum physics said that nothing is ever perfectly still, not even empty space. Energy fluctuates, particles appear and disappear. Uncertainty is built into the universe at a fundamental level. These ideas worked extremely well in laboratories and experiments. They described atoms, particles, and forces with incredible accuracy, but they were usually kept separate from gravity. Gravity ruled the large. Quantum physics ruled the small. Black holes sit at the boundary between these worlds. They are massive objects governed by gravity, but they also involve extremely small scales near their edges. For a long time, physicists avoided combining these ideas too deeply because the math became difficult and the concepts uncomfortable. As a result, black holes were mostly treated using classical gravity alone. Under that treatment, they were eternal. The mystery begins exactly here. If quantum physics says empty space is active and restless, and if gravity near a black hole is extreme, what happens when these two truths meet? What happens to the restless activity of empty space right at the event horizon? Does it simply stop? Or does the black hole's gravity change the rules? Before Stephen Hawking, most physicists assumed the rules did not change in any dramatic way. The event horizon was treated as a simple boundary. Nothing special happened there locally. A falling observer would cross it without noticing anything unusual. And since nothing could escape from inside, the outside universe would never see any effect coming from the black hole itself. The black hole was sealed. End of story. That is why Hawking's idea was so shocking. He did not claim that something escaped from inside the black hole. He did not say information leaked out through cracks or tunnels. Instead, he suggested something far more subtle. That the presence of the event horizon itself, combined with quantum effects, could allow energy to escape without violating the rule that nothing comes out from inside. This was a completely new way of thinking. It kept the idea of nothing escapes intact, while still allowing black holes to lose energy. At this stage, that idea sounds impossible. If nothing escapes, how could anything come out? This question is not a trick, it is the core mystery, and it is exactly where this story becomes interesting. The answer does not involve breaking the event horizon. It involves rethinking what empty space really is and how gravity changes its behavior. Stephen Hawking was not introduced to the world as a legend. He did not begin his career trying to overthrow established ideas or shock the scientific community. In fact, his early life looked fairly ordinary for a young man interested in science. He was born in England, curious, playful, sometimes rebellious, and not especially known as a prodigy. He enjoyed building things, thinking deeply, and questioning how the world worked. But he was not immediately seen as someone who would change our understanding of the universe. What made Hawking different was not that he knew more equations than everyone else, but that he was willing to stare at the most uncomfortable questions and refuse to look away. He was deeply curious about beginnings and endings. How did the universe start? How does it evolve? And most importantly, what are the ultimate limits of nature? Hawking entered cosmology at a time when it was still a developing field. The universe itself was becoming a serious scientific subject, rather than a philosophical one. Scientists were beginning to understand that the universe had a history, that it expanded, and that it might have begun in a dramatic event we now call the Big Bang. Hawking became fascinated with these ideas, especially with situations where gravity becomes extreme. He studied singularities, places where known laws of physics seem to break down. Black holes were a natural part of this interest. They were not just exotic objects. They were places where gravity, space, and time reached their limits. For Hawking, black holes were not curiosities at the edge of physics. They were keys to understanding reality itself. Early in his career, Hawking worked on proving that singularities are unavoidable and under certain conditions. This meant that black holes and the Big Bang were not mathematical accidents. They were real predictions of Einstein's theory of gravity. This work strengthened the idea that black holes were genuine features of the universe, not just strange solutions on paper. At this stage, Hawking fully accepted the standard view of black holes. Like everyone else, he believed that nothing escaped them. He believed they were eternal. He believed they were cosmic dead ends. There was no rebellion here yet, only careful, rigorous thinking. Then something happened that changed Hawking's life in a much more personal way. In his early 20s, he was diagnosed with a rare motor neuron disease. Doctors told him he had only a short time to live. Slowly, his muscles weakened. Walking became difficult. Speaking became difficult. Eventually, nearly all voluntary movement was lost. From the outside, it might have looked like the end of a scientific career before it truly began. But something unexpected happened instead. Faced with a limited future, Hawking became more focused, not less. He later said that once he realized he did not have much to lose, he felt freer to think boldly. His body was failing, but his mind was becoming sharper, more daring. Hawking's condition did not stop his thinking because thinking was the one thing that remained fully free. He could not run experiments or work with complex machinery, but theoretical physics did not require that. It required imagination, logic, and the ability to follow ideas wherever they led. Hawking spent long hours thinking deeply, visualizing concepts in his mind, and questioning assumptions others took for granted. His physical limitations forced him to simplify problems mentally, to focus on the core ideas rather than technical details. This may have helped him see things others missed. At the time, black hole physics was considered mostly settled. The equations of general relativity described black holes cleanly. They had mass, charge, and spin. They absorbed everything and emitted nothing. Most physicists believed the story was finished. Hawking did not accept that sense of finality. He noticed that black holes sat at the intersection of two powerful but incompatible theories. General relativity described gravity beautifully. Quantum physics described particles and uncertainty beautifully. But no one really understood what happened when these two theories met. Black holes were exactly the place where they met. Hawking began to wonder about the event horizon itself, not the inside of the black hole, but the boundary. According to classical physics, the event horizon was not special locally. A falling observer would cross it without noticing anything unusual, but Hawking asked whether this was still true once quantum effects were considered. He knew that quantum physics treats empty space very differently than classical physics does. Empty space, according to quantum theory, is alive with activity. Particles appear and disappear constantly. Energy fluctuates. Nothing is ever perfectly still. This is where Hawking did something dangerous, at least by scientific standards. He questioned an assumption that almost everyone accepted without hesitation. He asked whether a black hole placed in a quantum universe could really remain completely silent. He did not start by assuming black holes emit radiation. In fact, he expected to prove the opposite. His original goal was to show that black holes do not radiate, even when quantum effects are included. He believed the standard picture would survive. But as he followed the math and the logic, he began to see something unexpected. Hawking realized that the presence of an event horizon changes how quantum fields behave. The horizon divides space into regions that cannot communicate. This separation alters what different observers see as empty space. What looks like nothing to one observer can look like particles to another. This was a deeply unsettling idea, because it suggested that particle creation was not absolute. It depended on perspective. Near a black hole, the distinction between particles and empty space became blurred. As Hawking worked through the consequences of this, he reached a conclusion that surprised even him. Black holes should emit radiation, not because anything escapes from inside, but because the horizon itself, interacting with quantum fluctuations, creates a steady flow of energy outward. The black hole loses mass as a result. Over time, it shrinks. Given enough time, it disappears completely. This result went directly against decades of accepted wisdom. It challenged the idea that black holes are eternal. It challenged the idea that they have zero temperature. It challenged the idea that they are perfect prisons. When Hawking first presented this idea, the reaction was shock and skepticism. Black holes emitting radiation sounded like a contradiction. How could something defined by the fact that nothing escapes end up glowing? Many physicists initially believed there must be a mistake. Hawking himself was cautious. He knew the implications were enormous. If black holes radiate, then the laws of thermodynamics apply to them. They have temperature. They have entropy. They evolve. This meant black holes were not dead ends. They were dynamic objects. The most disturbing implication came later. If black holes evaporate, what happens to the information about everything that fell into them? Quantum physics says information is never destroyed, but if a black hole disappears, classical thinking suggests the information is gone forever. This conflict became known as the black hole information paradox. Hawking initially believed information was lost, a position that sparked decades of debate. Even today, this question remains one of the deepest unsolved problems in physics. What made Hawking's work so powerful was not just the result, but the way he arrived at it. He did not reject existing theories. He respected them deeply. He simply followed their logic into a place no one had fully explored. He showed that questioning basic assumptions does not weaken science, it strengthens it. Black holes were thought to be eternal because no one had asked whether empty space itself might behave differently near an event horizon. Hawking asked that question. Stephen Hawking became famous not only because of his ideas, but because of what he represented. A mind that refused to be limited by physical boundaries. A scientist who was willing to accept strange conclusions if the reasoning demanded it. His work on Hawking radiation transformed black holes from static monsters into evolving objects. It reminded scientists that even the most confident theories must remain open to challenge. The moment Hawking asked whether black holes could radiate was the moment certainty ended. It was a quiet question, asked on paper and in thought, not in dramatic speeches, but it changed everything. It turned black holes from eternal prisons into temporary structures. It connected gravity, quantum physics, and thermodynamics in a single idea, and it showed that the universe still holds surprises, even in places we thought we understood completely. When most people hear the phrase empty space, they imagine a perfect void, a place with nothing in it. No matter, no energy, no activity, just silence and darkness stretching forever. This idea feels natural because in everyday life, empty means empty. An empty room has nothing inside it. An empty box contains nothing. For a long time, scientists also thought of space this way. They imagined space as a passive background, a stage on which stars, planets, and galaxies move. Space itself was not considered active. It was just there. But modern physics revealed something deeply surprising. Space is not truly empty, not anywhere, not even in the darkest regions between galaxies. What we call empty space is actually one of the most restless, energetic things in the universe. This strange idea comes from quantum physics, the branch of science that describes how reality behaves at very small scales. Quantum physics does not see the universe as smooth and calm. It sees it as fuzzy, uncertain, and constantly fluctuating. According to quantum theory, you can never remove all energy from a region of space. Even at the lowest possible energy state, there is still motion. This leftover activity is known as quantum fluctuation. It means that space itself has a built-in restlessness. You can think of it as a kind of background vibration that never fully stops. One of the most helpful ways to imagine this is to think of empty space like a boiling surface, even though it does not look like one. Imagine water heating in a pot. Before it boils, tiny bubbles begin to form and collapse. They appear for a moment, then disappear. They pop into existence and vanish again. According to quantum physics, something similar happens in empty space all the time. Tiny particles appear out of nowhere, exist briefly, and then disappear again. These are called virtual particles. Virtual particles are not particles you can catch or measure directly. They're temporary disturbances in energy. They exist for such a short time that they usually leave no trace. The universe allows them to exist briefly as long as they disappear quickly. This is allowed because of a rule called the uncertainty principle, which says that energy can fluctuate for short periods without violating the laws of physics. The shorter the time, the larger the allowed fluctuation. As a result, space is constantly filled with these tiny bursts of activity. These virtual particles almost always appear in pairs. One particle and its opposite. For example, a particle and an antiparticle. They appear together like two bubbles forming at the same moment. Almost instantly, they collide and cancel each other out. When they annihilate, they return their energy back to space, leaving nothing behind. This process happens everywhere, constantly. In the space between stars, in the space inside atoms, even in the space inside your own body. We do not notice it because it happens on scales far too small and far too fast for human senses. In most situations, these particle pairs are harmless. They appear, disappear, and the universe goes on unchanged. But their existence tells us something important. Empty space is not nothing. It is a dynamic system governed by rules that allow constant activity. This alone was a radical shift in how scientists viewed reality. Space was no longer a passive stage, it was an active participant. For a long time, this strange behavior of empty space was studied mostly in laboratories and theoretical models. It helped explain effects like the behavior of atoms and forces between particles. But its connection to gravity was not fully explored. Gravity, after all, deals with large masses and large distances. Virtual particles seemed tiny and irrelevant by comparison. That assumption worked well in most cases. But black holes are not most cases. Near a black hole, gravity becomes extreme. Space and time are stretched, twisted, and distorted in ways that do not occur anywhere else. The closer you get to a black hole, the more intense these effects become. At the event horizon, the boundary of the black hole, gravity affects time so strongly that what counts as before and after becomes unclear. This matters deeply for virtual particles because their existence is tied to time. Remember that virtual particles exist only briefly. Their appearance and disappearance are measured in time. If time itself behaves differently, then the rules governing these particles may change as well. This is the key insight that later became crucial for understanding Hawking radiation. Near a black hole, empty space is not just restless, it is restless in a distorted way. Imagine those popping bubbles again, but now imagine the surface they appear on is being stretched unevenly. Some bubbles are pulled in one direction, while others are pushed away. Near a black hole, gravity can separate particle pairs before they have a chance to cancel each other out. One particle can be pulled inward toward the black hole, while the other is pushed outward into space. When this separation happens, the usual annihilation does not occur. The pair does not disappear together. One particle is lost to the black hole. The other escapes. This is why understanding empty space is essential for understanding Hawking radiation. Hawking did not imagine particles escaping from inside the black hole. Instead, he focused on what happens just outside it. The radiation comes from the behavior of empty space itself. The black hole's gravity alters the normal rules, allowing some of the universe's background activity to become visible. This idea also reveals something profound about the universe. It shows that even nothingness responds to gravity. Space is not separate from matter and energy. It is woven into the same fabric. When gravity becomes strong enough, it can turn invisible processes into real effects. It can turn fleeting fluctuations into lasting particles. Another important point is that this activity is not rare or special. The universe is always active. even where there are no stars, no galaxies, and no matter at all. In the vast dark regions between galaxies, space still hums with quantum activity. Virtual particles still appear and disappear. Energy still fluctuates. The universe never truly rests. There is no absolute stillness. This challenges a very old human intuition. We like to think in terms of solid things and empty gaps between them. But the universe does not work that way at its deepest level. There are no truly empty gaps. There are only regions with different kinds of activity. Some regions are filled with matter and light. Others are filled only with subtle fluctuations, but all of them are alive with physical processes. Understanding this helps explain why Hawking radiation was even possible as an idea. If space were truly empty, black holes would indeed be eternal. There would be nothing near them. That could change. But because space itself is active, black holes are embedded in a sea of quantum motion. They cannot isolate themselves completely from the universe around them. The event horizon does not block the activity of empty space. It reshapes it. This also explains why Hawking radiation is so weak. The effects involved are incredibly subtle. The particles involved come from tiny fluctuations. The energies are extremely small, especially for large black holes. The radiation is not dramatic or violent. It is quiet and slow, but over enormous spans of time, even tiny effects add up. The universe is patient. Empty space, once thought to be nothing, turns out to be the foundation of everything. It is where particles are born, forces act, and even black holes slowly lose their grip. This realization forces us to rethink what existence itself means. Something does not need to be visible or solid to be real. The deepest processes shaping the universe often happen in places that look empty to us. When people imagine a black hole, they often picture a dark sphere floating in space, like a giant cosmic ball with a hard surface. It feels natural to imagine that somewhere there must be an edge you could touch, a boundary where space suddenly ends and the black hole begins. But this picture is misleading. A black hole does not have a surface in the usual sense. There is no solid shell, no wall, no physical barrier you could bump into. Instead, the true boundary of a black hole is something far stranger and more subtle. It is called the event horizon, and understanding it is essential to understanding everything that follows, including Hawking radiation. The event horizon is best described as a boundary of possibility. It is not made of matter. It does not exist as a physical object. It is defined entirely by motion and limits. More specifically, it is the boundary beyond which escape becomes impossible. Outside the event horizon, it is still possible, at least in principle, to move away from the black hole. Inside it, every possible path leads inward. Once crossed, there is no route back out. Not because something blocks the way, but because space and time themselves are arranged so that escape is no longer an option. To make this idea clearer, imagine space not as empty air, but as a flowing landscape. A helpful everyday analogy is a river moving toward a waterfall. Far from the waterfall, the current is gentle. You can swim against it if you want. As you get closer, the current speeds up. Eventually, there is a point where the water flows faster than you can swim. No matter how strong you are, you cannot move upstream anymore. That point is not a wall. There is no sudden drop, but it marks a clear boundary. Cross it, and your fate is sealed. The event horizon is like that point, but instead of water flowing through space, it is space itself flowing inward. This is why the event horizon is not a physical surface. You would not feel anything special at the exact moment you crossed it, especially if the black hole were large. There would be no shock, no sudden darkness, no warning sign. Locally, the laws of physics behave normally. Your body would not suddenly be crushed or burned at the horizon itself. The event horizon is invisible and intangible. It exists because of how gravity reshapes the paths that light and matter can take. The key to this is light. In physics, Light defines what is possible. Light sets the maximum speed at which information and influence can travel. If light cannot escape from a region, then nothing else can either. The event horizon is defined as the place where even light cannot move outward. At that boundary, the inward pull of gravity becomes so strong that all possible directions forward lead deeper into the black hole. From the outside, it looks like light freezes at the edge. From the perspective of someone falling in, light continues to move normally. This difference in perspective is one of the reasons black holes feel so strange. Near the event horizon, gravity does more than pull objects inward. It also changes how time flows. According to Einstein's theory of gravity, time slows down in strong gravitational fields. The stronger the gravity, the slower time passes compared to regions farther away. Near a black hole, this effect becomes extreme. To a distant observer, a clock near the event horizon appears to tick more and more slowly. As an object approaches the horizon, it seems to freeze in time, fading and redshifting, never quite crossing. This does not mean it actually stops. It means that signals from it take longer and longer to reach the outside world. This strange behavior of time is not an illusion or a trick of measurement. It is a real feature of space-time. Time and space are linked, and near a black hole, both are severely distorted. For someone falling toward the black hole, time feels normal. Their watch ticks normally. They cross the event horizon without noticing anything special. But for someone watching from far away, the infalling object never seems to cross. This split in perspectives is not just confusing, it is fundamental. Both views are correct within their own frames of reference. This extreme stretching of time near the event horizon is one of the reasons this boundary is so important for Hawking radiation. Quantum processes depend on time. Virtual particles appear and disappear within extremely short time intervals. When time behaves differently for different observers, the definition of what counts as a particle can change. What looks like empty space to one observer may look like a stream of particles to another. The event horizon creates exactly this kind of situation. Another important feature of the event horizon is that it divides the universe into two regions that cannot communicate. Signals from inside cannot reach the outside. This separation is absolute. It is not like a door that could be opened or closed. It is a one-way boundary built into the structure of space-time itself. This makes the event horizon fundamentally different from any boundary we encounter in everyday life. It is not a thing. It is a rule. Because of this, the event horizon was long considered boring from a physical point of view. Physicists believed nothing interesting happened there locally. It was just a boundary marking where escape ended. The real drama, they thought, happened deep inside the black hole, near the center. The horizon itself was treated as passive. This assumption held for decades and seemed reasonable under classical physics. But when quantum physics enters the picture, this assumption breaks down. Quantum physics is sensitive to boundaries. It cares about how regions of space are divided. The event horizon is an extreme boundary, one that permanently separates cause and effect. This makes it a place where quantum behavior can change in subtle but important ways. Near the event horizon, the vacuum of space is no longer the same as it is far away. Because time flows differently, what counts as a short-lived fluctuation near the horizon can look like a longer-lasting effect to a distant observer. Virtual particle pairs that would normally appear and disappear harmlessly can be affected by the strong gravitational field. One particle may fall inward, while the other escapes outward. The horizon makes this separation possible because it prevents the two regions from reconnecting. This is why the event horizon is the key to Hawking radiation. The radiation does not come from the inside of the black hole. It comes from just outside the horizon. It is created by the interaction between quantum fluctuations and the distorted space-time near this boundary. Without an event horizon, there would be no Hawking radiation. A massive object without a horizon would not produce the same effect. The horizon is essential because it creates a permanent divide that allows energy to flow outward in a subtle way. It is important to emphasize that nothing actually escapes from inside the black hole. The old rule still holds. The event horizon is not violated. Hawking radiation respects the boundary completely. The particles that escape are created outside the horizon. The black hole loses energy because the escaping particles carry it away, and that energy must come from the black hole's mass. The horizon itself remains intact. It does not leak or crack. It simply reshapes how space and time behave nearby. This subtlety is why Hawking radiation was so difficult to discover and accept. It does not involve dramatic explosions or obvious violations of known laws. It arises from quiet, almost invisible effects that only become clear when gravity and quantum physics are considered together. The event horizon, once thought to be a dull boundary, turns out to be an active player in the universe's story. The event horizon also forces us to rethink what we mean by location and reality. It shows that what exists can depend on who is observing. Particles, time, and even temperature can appear differently depending on perspective. This is deeply uncomfortable for our everyday intuition, which prefers a single, objective picture of the world. But the universe does not care about comfort. It follows its own rules, even when they clash with human expectations. At first glance, Hawking radiation sounds like a contradiction. A black hole is defined by the idea that nothing escapes it. Hawking radiation, on the other hand, says black holes emit energy. It feels like one of these ideas must be wrong. But the power of Hawking's insight is that neither idea is broken. The rule that nothing escapes from inside a black hole remains true. Hawking radiation works without violating that rule. The explanation is subtle, quiet, and deeply connected to the strange behavior of empty space near the event horizon. To understand the simple idea behind Hawking radiation, we return to something we have already discussed. Empty space is not truly empty. It is filled with constant activity. Tiny particle pairs appear and disappear everywhere in the universe. They exist for an incredibly short time and then vanish again, returning their energy back to space. This happens constantly and normally has no lasting effect. Space remains stable because these particles cancel each other out almost instantly. These particles always appear in pairs, one particle and its opposite. You can imagine them like two bubbles forming at the same moment. One has positive energy, the other negative. In a very specific quantum sense, under normal conditions, they annihilate each other immediately. They meet, cancel out, and leave nothing behind. No energy is gained or lost overall. This balance is what keeps empty space from boiling over into chaos. Now imagine this process happening very close to the event horizon of a black hole. This is where things change. The event horizon is not a surface, but it is a boundary that divides the universe into two regions that cannot communicate. Gravity near this boundary is incredibly strong. Space and time are stretched in extreme ways. Because of this, the usual fate of particle pairs can be disrupted. If a particle pair appears far from a black hole, nothing special happens. They annihilate each other as usual. But if a particle pair appears right at the edge of the event horizon, the black hole's gravity can pull them apart before they have a chance to disappear together. One particle may be pulled inward, crossing the event horizon, while the other is pushed outward into space. This is the heart of the particle pair explanation. One particle falls into the black hole, the other escapes. The escaping particle becomes real. It no longer disappears after a brief moment. It travels outward and can, in principle, be detected far away. This outward moving particle is what we call Hawking radiation. At this point, a natural question arises. If a particle escapes, where does its energy come from? Energy cannot come from nothing. Physics does not allow free energy to appear without a source. The answer is that the energy comes from the black hole itself. To see why, we need to think carefully about what happens to the particle that falls in. In quantum physics, particles can have what is called negative energy relative to an outside observer. This does not mean the particle is weird or magical. It means that in the warped space-time near a black hole, the definition of energy changes. The particle that falls into the black hole carries negative energy relative to the outside universe. When this negative energy particle enters the black hole, it reduces the total energy of the black hole. In other words, the black hole loses mass. This is a crucial point. The black hole does not lose mass because something escapes from inside it. It loses mass because it absorbs something with negative energy. At the same time, the escaping particle carries positive energy away. The total energy of the universe is conserved. Nothing is created from nothing. The books still balance. This is why Hawking radiation does not violate physics. It respects the conservation of energy. It respects the event horizon. It respects the rules of quantum mechanics and gravity. It simply reveals a subtle interaction between them that was not previously understood. As this process repeats over time, the black hole continues to lose mass. Each escaping particle carries away a tiny amount of energy. Each infalling negative energy particle slightly reduces the black hole's mass. The effect is incredibly small for large black holes. For a black hole with the mass of the Sun, the radiation is so weak that it is completely overwhelmed by other sources of energy, like the cosmic background radiation. Such a black hole actually absorbs more energy from its surroundings than it emits. But the process never stops. Given enough time, and if the universe becomes cold and empty enough, Hawking radiation will dominate. The black hole will slowly shrink. Its event horizon will gradually get smaller. As the black hole shrinks, something interesting happens. Smaller black holes radiate more strongly than larger ones. This means that as a black hole loses mass, it begins to evaporate faster and faster. This leads to a long quiet phase followed by a dramatic ending. For most of its life, a black hole changes very slowly. Trillions upon trillions of years can pass with almost no noticeable difference. But near the very end, when the black hole has become extremely small, the radiation becomes intense. The black hole releases its remaining energy in a final burst before disappearing completely. What exactly happens at this final moment is still not fully understood, but the general picture is clear. Black holes are not eternal, they are temporary. It is important to emphasize how slow this process is. Hawking radiation is not something you would ever see happening in real time for a stellar mass black hole. The timescales involved are far beyond human imagination. A black hole with the mass of the Sun would take far longer than the current age of the universe to evaporate. Supermassive black holes like the ones at the centers of galaxies would take even longer. They will likely be among the last objects to exist in the universe. Despite its weakness, Hawking radiation has enormous importance. It tells us that black holes have a temperature. They are not perfectly cold. This temperature depends on their mass. Large black holes are extremely cold. Small black holes are hot. This connects black holes to thermodynamics, the science of heat and energy. It shows that black holes obey the same general laws as other physical systems, even though they are extreme. The simplicity of the particle pair explanation makes Hawking radiation easier to imagine, but it is important to understand that it is a picture, not a literal description. In reality, the process is more subtle and involves quantum fields rather than individual particles popping into existence like tiny objects. But the picture captures the essential idea. The event horizon disturbs the vacuum of space. That disturbance leads to a steady leakage of energy. What makes this idea so powerful is that it emerges naturally once quantum physics and gravity are combined. Hawking did not invent new laws to make black holes evaporate. He simply applied existing laws to a situation where they had not been fully explored. The result was surprising, but it was not arbitrary. It followed logically from the rules of the universe. This also explains why Hawking radiation was so shocking. Black holes had been treated as simple objects for decades. They were seen as endpoints, not processes. Hawking radiation turned them into evolving systems. It showed that black holes have lifetimes, temperatures, and even something like aging. They are not frozen in time. They participate in the long story of the universe. The idea also forces us to rethink what we mean by nothing escaping. Nothing escapes from inside the black hole, and that rule still holds. Hawking radiation does not sneak information or matter out through hidden doors. Instead, it comes from the interaction between the black hole and the quantum vacuum outside it. The black hole loses mass not by leaking, but by absorbing negative energy. This distinction matters deeply for understanding why the theory remains consistent. When people hear the word radiation, they often think of fire, glowing heat, or dangerous energy pouring out in bright flashes. We associate radiation with things we can feel or see, like the warmth of the sun on our skin or the glow of a hot stove. This makes it sound strange, even wrong, to say that black holes radiate. Black holes are dark by definition. They do not burn fuel. They do not shine like stars. They have no surface where heat can build up and escape. And yet, Hawking radiation tells us that black holes glow in a very real physical sense, even though there is no fire involved. To understand how this is possible, we need to rethink what radiation really means. In physics, radiation does not require flames or brightness. Radiation simply means energy being carried away through space. That energy can take many forms. It can be visible light, like sunlight. It can be invisible, like radio waves, X-rays, or gamma rays. It can even take the form of particles. What matters is not how dramatic it looks, but whether energy is moving outward from an object. Hawking radiation is radiation in this broad technical sense. It is energy escaping into space, not from burning matter, but from the behavior of empty space near a black hole's event horizon. This is why Hawking radiation is fundamentally different from the radiation produced by stars. A star shines because it has a hot surface. Nuclear reactions in its core release energy, which slowly moves outward. That energy heats the star's outer layers until they glow. The light we see from a star comes from real atoms emitting photons as they cool. A black hole has none of this. It has no surface, no atmosphere, and no internal furnace. There is nothing inside a black hole that can glow in the usual sense. The radiation associated with black holes comes from outside, not from within. Hawking radiation does not come from the black hole's interior. It comes from the region just outside the event horizon. It is produced by the interaction between strong gravity and quantum fluctuations in empty space. This is why it is often described as a kind of quantum glow. It is not caused by heat in the traditional sense. It is caused by the structure of space-time itself. Despite this difference, physicists still use the concept of temperature to describe black holes. This may seem confusing at first. Temperature usually measures how hot something is, how much its particles are moving. But in physics, temperature has a deeper meaning. It is a measure of how much energy is associated with random motion or uncertainty. Hawking showed that black holes behave as if they have a temperature. This temperature is not felt as warmth, but it determines how much radiation they emit. The temperature of a black hole depends on its mass. This is one of the most surprising results of Hawking's work. For ordinary objects, larger things tend to hold heat longer and cool more slowly, but their temperature does not automatically depend on their size. For black holes, the relationship is much more direct. The more massive a black hole is, the lower its temperature. Large black holes are extremely cold. Small black holes are much hotter. This inverse relationship feels counterintuitive. We might expect a more massive object to be more energetic, but black holes do not behave like ordinary objects. Their temperature is linked to the strength of gravity at the event horizon. Smaller black holes have stronger curvature of spacetime near their horizons. This leads to more intense quantum effects and stronger Hawking radiation. Larger black holes have gentler curvature at their horizons, which leads to weaker radiation. To put this into perspective, consider a black hole with the mass of the Sun. Its temperature, due to Hawking radiation, would be far colder than the temperature of deep space. It would be billions of times colder than the cosmic background radiation that fills the universe. This means that such a black hole actually absorbs more energy from its surroundings than it emits. In practical terms, it does not appear to glow at all. Its Hawking radiation is completely drowned out by the environment. Supermassive black holes like the ones found at the centers of galaxies are even colder. They are among the coldest objects in the universe. Their Hawking radiation is so weak that it is essentially undetectable. These black holes will remain massive and dark for unimaginably long periods of time. They will outlive stars, galaxies, and possibly even most other structures in the universe. Small black holes, on the other hand, behave very differently. If a black hole were much smaller than those formed by collapsing stars, its Hawking radiation would be much stronger. As a black hole shrinks, its temperature rises. This creates a kind of feedback loop. The smaller the black hole becomes, the more radiation it emits. The more radiation it emits, the faster it loses mass. Near the end of its life, a very small black hole could become extremely hot, releasing large amounts of energy in a short time. This does not mean black holes explode like bombs in the usual sense, but it does mean that their final moments could be dramatic. Exactly what happens at the very end of a black hole's evaporation is still an open question. Our current theories are not complete enough to describe this final stage with certainty, but the general trend is clear. Black holes do not fade gently forever. Their end, while delayed for an incredibly long time, may be sudden. The idea that black holes have temperature also connects them to the laws of thermodynamics. These laws describe how energy flows and how systems evolve over time. Hawking radiation shows that black holes follow these laws too. They are not exceptions. They have entropy, which measures how much information is hidden inside them. They have temperature, which determines how they exchange energy with their surroundings. And they evolve, slowly changing over time. This was a major shift in how black holes were understood. Before Hawking, black holes were seen as simple objects, described by only a few numbers. After Hawking, they became thermodynamic systems with rich internal structure, even if that structure is hidden behind an event horizon. This change in perspective had deep consequences for theoretical physics and for our understanding of the universe as a whole. One of the most important consequences is the realization that black holes are not perfectly dark in an absolute sense. They glow, but in a way that is almost impossible to notice. Their glow is not visual. It is not something eyes or telescopes can easily see. It is a faint quantum whisper rather than a blazing light. And yet, over enough time, that whisper can erode even the most massive objects. Most black holes today are incredibly cold because the universe itself is still relatively warm. The background radiation left over from the Big Bang fills space with low-level energy. Black holes absorb this energy faster than they lose energy through Hawking radiation. Only in the very distant future, when the universe has expanded and cooled even further, will black holes begin to truly lose mass overall. That future lies so far ahead that it stretches beyond almost any human timescale we can imagine. Understanding why black holes glow without fire helps remove the last sense of contradiction from Hawking radiation. The glow is not a sign of burning or leaking. It is a natural consequence of how space, time, and quantum physics interact at extreme boundaries. Black holes do not shine like stars, but they are not completely silent either. They participate in the universe's energy balance in their own subtle way. Time feels simple in everyday life. Seconds pass, clocks tick. Yesterday becomes today, and today becomes tomorrow. No matter where you are or what you're doing, time seems to move forward at a steady, universal pace. This intuition is so strong that it feels obvious and unquestionable. But near a black hole, this idea completely breaks down. Time does not flow the same way everywhere. It stretches, slows, and behaves in ways that feel deeply unnatural. To understand Hawking radiation more fully, we need to understand how extreme gravity reshapes time itself, and why this strange behavior of time plays a crucial role in how particles behave near black holes. According to Einstein's theory of gravity, gravity is not just a force pulling objects together, it is a distortion of space-time. Massive objects bend space and slow time. The stronger the gravity, the greater this effect. On Earth, gravity is relatively weak, so time flows almost uniformly. But even here, time moves slightly slower at sea level than on a mountain. This effect has been measured precisely using atomic clocks. It is small, but real. Near a black hole, this effect becomes enormous. As you approach a black hole, gravity grows stronger and stronger. Time slows down more and more, compared to time far away. Near the event horizon, this slowing becomes extreme. To a distant observer, a clock falling toward a black hole appears to tick more slowly as it approaches the horizon. Each second stretches longer than the last. Signals sent outward take longer and longer to arrive. Eventually, the clock appears to freeze, never quite reaching the horizon. This does not mean the clock actually stops. It means that the flow of time near the black hole is radically different from the flow of time far away. For the person falling toward the black hole, the experience is completely different. Their own clock ticks normally. Their thoughts move normally. Nothing strange seems to happen at the event horizon itself. This difference in perspective is not an illusion or a trick. Both descriptions are correct. Time is not absolute. It depends on the observer's position in a gravitational field. This is one of the most unsettling lessons of modern physics. Why does this matter for particle behavior? Because in quantum physics, time plays a central role. Virtual particles exist for very short periods of time. Their appearance and disappearance are governed by the uncertainty principle, which links time and energy. The shorter the time interval, the larger the energy fluctuation that is allowed. This is why virtual particles can appear briefly without violating the laws of physics. They borrow energy from time, so to speak, as long as they give it back quickly. Near a black hole, time does not behave uniformly. What counts as a short time near the event horizon can look very different to different observers. To someone far away, processes near the horizon appear stretched out. This stretching changes how quantum fluctuations appear. Virtual particles that would normally vanish too quickly to be noticed can, from the outside perspective, linger longer. This difference is crucial for understanding why Hawking radiation exists. The connection between time, energy, and radiation lies at the heart of this effect. Energy and time are deeply linked in quantum physics. When time is distorted, the energy landscape changes as well. Near a black hole, the extreme slowing of time allows energy fluctuations to behave differently. Particle pairs that would normally annihilate each other almost instantly can be separated by gravity before that happens. One particle falls inward, the other escapes outward. The stretching of time near the horizon makes this separation possible. This is not because the black hole is actively pushing particles out. It is because the geometry of space-time itself creates conditions where the normal balance of appearance and disappearance is disrupted. The black hole changes the rules by changing the stage on which those rules play out. Time is no longer uniform. Energy is no longer defined the same way everywhere. And because of this, radiation can emerge from what looks like empty space. Black holes are especially powerful at changing the rules of reality because they push gravity to its extreme limit. In most places in the universe, gravity is too weak to significantly affect quantum processes. The two worlds remain mostly separate. Near a black hole, they collide. Space-time becomes so distorted that concepts like before and after, inside and outside, particle and vacuum begin to blur. This does not mean reality breaks down. It means it behaves in ways we're not used to. One way to make sense of these strange effects is through everyday examples. Imagine standing on a moving walkway at an airport. If you walk forward on the walkway, you move faster relative to the ground. If you walk backward, you move slower. Now imagine the walkway speeding up as you move along it. At some point, even if you walk backward as fast as you can, the walkway carries you forward. This is similar to what happens near a black hole. Space itself is moving inward. Time itself is stretched. What seems like freedom of motion far away becomes inevitable motion inward near the horizon. Another useful analogy is a stretched rubber sheet. If you place a heavy object in the center, the sheet curves downward. A small ball rolled nearby will spiral inward. But imagine the sheet also stretches time. Near the heavy object, everything slows down. Movements take longer, vibrations last longer. Processes that would normally be brief become extended. This stretching allows subtle effects to accumulate. Near a black hole, quantum fluctuations are like tiny ripples on this sheet. The stretching of space-time allows those ripples to separate and persist. We can also think about time distortion using sound. Imagine a short clap echoing in a narrow canyon. The sound lingers longer than it would in an open field. The environment stretches the experience of the sound. Near a black hole, space-time acts like a canyon for quantum fluctuations. What would normally be a brief silent event becomes extended and meaningful. The key idea is that black holes do not create new rules of physics. They expose rules that are usually hidden. In everyday conditions, time flows smoothly enough that quantum fluctuations remain invisible. Near a black hole, time is stretched so dramatically that these fluctuations become part of the observable universe. Hawking radiation is not a violation of reality. It is reality behaving honestly under extreme conditions. This also explains why Hawking radiation depends so strongly on the black hole's size. Smaller black holes have stronger gravity near their horizons. Time is distorted more sharply. Quantum effects are stronger. Radiation is more intense. Larger black holes have gentler horizons. Time distortion is weaker. Radiation is fainter. The relationship between size, gravity, and time explains why most black holes glow so weakly. Understanding this interplay between time and gravity helps resolve the feeling that Hawking radiation is magical or mysterious in an unjustified way. It is strange, but it is not arbitrary. It follows naturally once we accept that time is flexible and that gravity reshapes it. When time slows down, energy behaves differently. When energy behaves differently, radiation can appear. For most of human history, black holes were imagined as permanent scars in the universe. Once formed, they would sit in space forever, growing larger as they swallowed matter, never weakening, never fading. This idea felt natural. Black holes are born from collapsing stars, and their gravity is so strong that even light cannot escape. It seems impossible that something so powerful could ever lose strength. And yet Hawking radiation quietly changes this picture. It suggests that black holes are not eternal. They slowly lose mass, shrink, and eventually disappear. The idea feels almost unbelievable, not because it's violent or dramatic, but because it is so patient and so slow. The way black holes lose mass is subtle. There is no tearing, cracking, or leaking of the event horizon. Nothing escapes from inside. Instead, mass is lost through the steady release of Hawking radiation from just outside the horizon. Each time a particle escapes into space, the black hole loses a tiny amount of energy. And because energy and mass are linked, Losing energy means losing mass. The black hole becomes slightly smaller. Its event horizon shrinks by an almost immeasurable amount. This process repeats again and again, endlessly, as long as the black hole exists. It is important to understand how small each step in this process really is. Hawking radiation is incredibly weak for black holes that form from stars. A black hole with the mass of the Sun loses such a tiny amount of mass per second that it would take far longer than the age of the universe to notice any change. Even after billions of years, it would be almost exactly the same size. This is why black holes still seem eternal in practice. On human timescales, and even on cosmic timescales so far, they barely change at all. The reason the process is so slow comes down to size. Large black holes have gentle gravity at their event horizons. The distortion of space-time there is strong enough to trap light, but not sharp enough to produce intense quantum effects. This means their Hawking radiation is extremely faint. In fact, the radiation is often weaker than the background energy of the universe itself. Right now, the universe is filled with low-level radiation left over from the Big Bang. Most black holes absorb more energy from this background than they emit through Hawking radiation. They are not shrinking at all. They are growing, or at least staying the same. Only when the universe becomes much colder and emptier will Hawking radiation truly begin to dominate. This will not happen for an unimaginably long time. As the universe expands, stars will burn out, galaxies will drift apart, and background radiation will thin and cool. Eventually, the environment around black holes will become so empty that they will no longer absorb more energy than they emit. At that point, the slow evaporation process will truly begin. When we say trillions upon trillions of years, we are not using the phrase casually. The timescales involved are almost impossible to visualize. 1 trillion years is 1,000 billion years. The universe today is about 14 billion years old. That means even 1 trillion years is nearly 100 times longer than the universe has existed so far. For a black hole with the mass of the Sun, the evaporation time is not just trillions of years, but vastly longer than that. Numbers become so large that writing them down loses meaning. The evaporation times are so extreme that even calling them long does not do them justice. Supermassive black holes take even longer to evaporate. The black holes at the centers of galaxies contain millions or billions of times the mass of the Sun. Their lifetimes are correspondingly longer. They will likely be the last large structures in the universe. Long after stars have gone dark and galaxies have faded into isolated islands, supermassive black holes will still remain, slowly and quietly radiating away their mass. Despite this extreme slowness, the process does not stall. Once a black hole truly begins to lose mass overall, it cannot stop. As it shrinks, its temperature rises. This causes it to emit radiation more strongly. The stronger radiation causes it to lose mass faster. This creates a slow feedback effect. For most of the black hole's life, this feedback is negligible, but near the very end, it becomes important. The final stages of black hole evaporation are the most mysterious. As the black hole becomes very small, its temperature rises dramatically. The radiation becomes intense. The black hole loses mass more and more quickly. Eventually, it reaches a point where our current theories can no longer describe what happens with confidence. The black hole is now so small that quantum gravity effects become important, and we do not yet have a complete theory of quantum gravity. What we can say is that the black hole does not simply fade away quietly forever. Its final moments may involve a sudden release of energy. This is not an explosion in the familiar sense like a bomb or a supernova, but it is a dramatic end compared to the long, silent evaporation that came before. The black hole releases its remaining energy and disappears. There is no leftover core, no remnant, just radiation spreading out into space. What does the universe look like after black holes fade away? To imagine this, we need to think far beyond the present era of stars and galaxies. In this distant future, stars have long since burned out. No new stars are forming. Galaxies have drifted apart beyond each other's reach. The universe is dark, cold, and nearly empty. Only faint radiation and isolated particles remain. Black holes, once the dominant objects of this era, slowly disappear one by one. Stellar mass black holes vanish first. Supermassive black holes are the last to go. When they finally evaporate, the universe enters a new phase. There are no more large concentrations of mass, no objects with strong gravity. The universe becomes smooth and diffuse, filled with low-energy particles and radiation. In this final era, change still happens, but it is incredibly slow. Particles drift, radiation stretches as space expands. Time loses its familiar meaning because nothing dramatic ever occurs. The universe becomes a place of quiet evolution rather than dynamic events. This is sometimes called the heat death of the universe, a state where usable energy has been spread out so evenly that nothing interesting can happen anymore. The idea that black holes die may feel unsettling, but it also carries a strange sense of closure. Black holes were once seen as places where the universe stored its secrets forever. Hawking radiation suggests that even these secrets eventually fade into the broader flow of cosmic history. Nothing is truly permanent. Not stars, not galaxies, not even black holes. Hawking radiation is one of the most famous predictions in modern physics. Yet there is a frustrating truth about it. We have never seen it directly. No telescope has captured it. No detector has clearly measured it coming from a real black hole in space. This can feel disappointing, especially for an idea that reshaped how scientists think about black holes and the universe. But the reason we cannot see Hawking radiation is not because the idea is weak or flawed. It is because the radiation itself is extraordinarily faint, drowned out by the much louder universe around it. The first and most important reason Hawking radiation is so hard to detect is its weakness. For black holes formed by collapsing stars, the amount of energy released through Hawking radiation is incredibly small. These black holes are massive, and as we have seen, massive black holes are extremely cold. Their temperature is far below the temperature of the surrounding universe. This means they emit very little radiation. The energy carried away by Hawking radiation is so tiny that it has no noticeable effect on their surroundings, at least not on any time scale we can observe. To get a sense of how weak this radiation is, imagine trying to detect the warmth of a single candle placed on the moon while standing on Earth, with the sun shining brightly in the sky. Even that comparison does not fully capture how difficult the task is. Hawking radiation from a stellar mass black hole is many orders of magnitude weaker than most sources of energy in space. It is not just faint, it is almost completely buried beneath other signals. This leads to the second problem. Telescopes are simply not designed to detect something this subtle. Telescopes, whether they observe visible light, radio waves, X-rays or gamma rays, are built to catch strong, distinct signals. They are excellent at spotting stars, galaxies, supernova, and energetic events. Hawking radiation does not announce itself with a clear signature. It does not produce a sharp flash or a unique pattern that stands out easily from the background. Even our most sensitive instruments would struggle to separate it from noise. Another challenge is distance. The black holes we can observe are incredibly far away. The nearest known black holes are still thousands of light years from Earth. Any Hawking radiation they emit spreads out as it travels through space, becoming even weaker by the time it reaches us. By the time it arrives, if it arrives at all, it is indistinguishable from the faint hum of radiation that fills the universe. That background hum is the next major obstacle. Space is not quiet. It is filled with radiation from many sources. One of the most important is the cosmic microwave background. the faint afterglow of the Big Bang. This radiation fills all of space and has a temperature just a few degrees above absolute zero. Even this weak background radiation is much stronger than the Hawking radiation emitted by most black holes today. In fact, for many black holes, the situation is reversed. They absorb more energy from the cosmic background radiation than they emit through Hawking radiation. Instead of shrinking, they are slowly gaining energy. This makes direct detection even more difficult. Any attempt to observe Hawking radiation must first separate it from this ever-present background, which is like trying to hear a whisper in the middle of a crowded stadium. There is also the issue of confusion with other astrophysical processes. Black holes are often surrounded by glowing matter. Gas and dust falling toward a black hole heat up and emit intense radiation. This radiation is extremely bright compared to Hawking radiation. It dominates everything we see around black holes. Even if Hawking radiation were present, it would be completely overwhelmed by this brighter emission. We cannot simply point a telescope at a black hole and expect to see its quantum glow. The environment around it is far too noisy. Because of these challenges, scientists have had to be creative. If we cannot observe Hawking radiation directly in space, can we recreate similar conditions in the laboratory? This question has led to a fascinating area of research. Physicists have built systems that behave mathematically like black holes, even though they are not gravitational objects. These are sometimes called analog black holes. One example involves sound waves instead of light. In certain materials, scientists can create regions where sound cannot escape, similar to how light cannot escape a black hole. These systems have horizons of their own, known as acoustic horizons. In these laboratory setups, researchers have observed effects that closely resemble Hawking radiation, but with sound waves instead of photons. Tiny fluctuations near the horizon produce measurable signals, just as Hawking predicted. Other experiments use light in optical fibers, flowing fluids, or ultra-cold gases. In each case, the goal is the same: create a boundary that mimics an event horizon and study how quantum fluctuations behave near it. While these experiments do not prove that real black holes emit Hawking radiation, they strongly support the underlying physics. They show that, horizons of many kinds can produce radiation-like effects through quantum processes. These laboratory experiments are important because they test the logic of Hawking's idea in controlled settings. They show that the mechanism behind Hawking radiation is not unique to black holes. It arises whenever a horizon separates regions of space in a particular way. This gives scientists confidence that the effect is real, even if it remains unobserved in space. Indirect evidence also matters deeply in science. Many important ideas were accepted long before they could be directly observed. Gravitational waves were predicted a century before they were detected. Atoms were taken seriously long before they could be seen individually. Black holes themselves were accepted decades before we had direct images of them. Hawking radiation sits in this tradition. Its strength lies in how naturally it emerges from well-tested theories. Hawking radiation is not an isolated guess. It follows from combining quantum physics and gravity in a careful way. Both of these theories have been tested extensively in their own domains. When they overlap near an event horizon, Hawking radiation appears almost inevitably. This theoretical consistency is powerful evidence. It suggests that the radiation is not a mistake, but a genuine feature of reality. There is also another kind of indirect support. Hawking radiation fits beautifully with the laws of thermodynamics. It gives black holes a temperature and an entropy. It makes them behave like physical systems rather than mysterious exceptions. This unification is a strong sign that the idea is on the right track. Nature tends to favor consistency, not special cases. Future technology may eventually allow more direct tests. If tiny black holes formed in the early universe exist, they might emit stronger Hawking radiation today. Detecting signals from such objects would be extraordinarily difficult, but not completely impossible in principle. Advances in detectors, data analysis, and observational techniques may one day reveal hints of Hawking radiation hidden in cosmic data. For now, the fact that we cannot see Hawking radiation directly does not weaken its importance. Instead, it highlights how subtle the universe can be. Some of the most profound processes happen quietly, beneath layers of noise and distraction. Hawking radiation is not meant to be obvious. It operates on scales of time and energy that stretch beyond everyday experience. One of the deepest and most unsettling questions raised by Hawking radiation is not about energy or particles, but about information. At first, this may sound abstract. Information feels like something related to computers, books, or memories, not black holes. But in physics, information has a very precise meaning. It refers to the complete description of a physical system. If you know the information about something, you can, in principle, predict how it will behave in the future. The question of whether Hawking radiation destroys information cuts straight to the heart of what reality allows and what it forbids. To understand the problem, we need to start with a simple idea. In modern physics, information is never supposed to be destroyed. This principle comes from quantum mechanics, which governs the behavior of particles at the smallest scales. According to quantum theory, the laws of physics are reversible. If you know the exact state of a system at one moment, you can, in principle, run the equations backward and reconstruct the past. Information might get scrambled, hidden, or spread out, but it is not erased. This rule is not just a preference, it is built into the mathematics of quantum physics. Black holes seem to challenge this rule long before Hawking radiation was proposed. When something falls into a black hole, all of its detailed features appear to vanish from the outside universe. It does not matter whether a star, a planet, or a book falls in. From the outside, the black hole looks the same, except for its mass, charge, and spin. All other details are lost behind the event horizon. This already made physicists uneasy, but as long as black holes were eternal, the problem could be avoided. The information was hidden, not destroyed. It was locked away forever inside the black hole. Hawking radiation changed everything. If black holes evaporate completely, then the information that fell into them seems to vanish along with them. The radiation emitted during evaporation appears to be random. It carries energy, but no obvious information about what went in. When the black hole is gone, nothing remains to store that information. It looks as if the information has been erased from the universe entirely. This apparent contradiction is called the black hole information paradox. The paradox can be stated simply. Quantum physics says information cannot be destroyed. Hawking radiation seems to destroy information. Both ideas come from solid, well-tested theories. They cannot both be correct in the same way at the same time. Something must give. Either our understanding of quantum mechanics is incomplete, our understanding of gravity is incomplete, or our picture of black holes is missing something crucial. Why does information matter so much? Because without information conservation, physics loses its predictability. If information can truly disappear, then the future cannot always be predicted from the past, even in principle. This would undermine the foundation of quantum theory. It would also break the connection between cause and effect at a fundamental level. Physics would become less like a rule-based system and more like a collection of approximations that fail in extreme situations. To see what seems to be lost, imagine throwing an encyclopedia into a black hole. The encyclopedia contains a huge amount of information: words, ideas, patterns. As it falls in, it is torn apart, heated, and eventually crosses the event horizon. From the outside, all of those details disappear. Later, the black hole emits Hawking radiation. But that radiation looks like random noise. It does not spell out words or encode obvious patterns. When the black hole finally evaporates, there is no trace of the encyclopedia left. It seems as if the information it contained has been destroyed. This is deeply troubling from a quantum point of view. Even if the encyclopedia were burned, its information would still exist in the motion of particles, the distribution of energy, and the radiation released. It would be scrambled but not erased. Black hole evaporation seems different. It looks like a clean deletion, something the universe is not supposed to allow. Stephen Hawking initially embraced this conclusion. He argued that black holes really do destroy information. According to his early view, quantum mechanics would have to be modified to accommodate this loss. He believed that gravity introduces a kind of fundamental randomness that makes information loss possible. This was a bold and controversial position. Many physicists disagreed strongly, insisting that quantum mechanics must remain intact. The debate became one of the most intense in modern theoretical physics. It was not just a technical disagreement, it was a clash over the basic nature of reality. Is the universe fundamentally predictable, or does it allow true erasure? Are black holes exceptions to the rules, or do they follow deeper rules we do not yet understand? Over time, Hawking's own views evolved. As research progressed, new ideas emerged that suggested information might not be destroyed after all. One key insight was that Hawking radiation might not be completely random. Subtle correlations between the particles emitted at different times could, in principle, encode information about what fell into the black hole. This information would not be easy to read or reconstruct, but it would still exist in a highly scrambled form. Hawking eventually accepted that information is likely preserved. He conceded that black holes do not destroy information completely. Instead, information may be returned to the universe through Hawking radiation in a form that is extremely difficult to decode. This shift in position was significant. It showed Hawking's willingness to change his mind in the face of new arguments and evidence. Even with this change, the problem is not solved. We still do not have a complete, clear description of how information escapes a black hole. We do not know how it is encoded in Hawking radiation or how the process respects both quantum mechanics and gravity. Several ideas have been proposed. Some suggest that information is stored on the event horizon itself, like data on a surface. Others propose that the interior of a black hole is somehow connected to the radiation outside in ways we do not yet fully understand. There are also radical ideas that challenge our basic assumptions. Some theories suggest that space-time itself emerges from information. Others propose that black holes are connected to other regions of the universe through subtle quantum links. These ideas are speculative, but they highlight how deep the problem runs. The information paradox is not just about black holes, it is about the nature of space-time, reality, and the limits of physical law. The question remains unsolved because we do not yet have a complete theory that unifies quantum mechanics and gravity. Hawking radiation sits at the intersection of these two frameworks. Each works extremely well in its own domain, but their combination is still incomplete. Without a full theory of quantum gravity, we cannot definitively answer what happens to information in black hole evaporation. What makes this question so important is that it acts as a guide. It tells physicists where current theories break down. It points toward the places where new ideas are needed. The information paradox has already led to major advances in theoretical physics, including new ways of thinking about entropy, space-time, and the holographic nature of the universe. Hawking radiation is often described as a detail about black holes, but its true importance goes far beyond that. It is not just a prediction about distant cosmic objects. It is a message about reality itself. It tells us that the universe is stranger, more subtle and less solid than it appears. At its core, Hawking radiation exposes a deep clash between two pillars of modern physics and forces us to confront the limits of our understanding. The clash begins with quantum physics and gravity. Quantum physics governs the smallest scales of reality. It describes particles, fields, uncertainty, and probabilities. It tells us that nature is fuzzy at its foundation, that particles do not have exact positions or energies until they are measured. Gravity, as described by Einstein's theory, governs the largest scales. It treats space-time as smooth and continuous, bending gently or violently, depending on how much mass and energy are present. For most of the universe, these two theories coexist peacefully because they operate in separate domains. Quantum effects dominate atoms and particles. Gravity dominates planets, stars, and galaxies. Black holes destroy this separation. They are massive objects with extreme gravity, but they also involve very small regions near their event horizons where quantum effects matter. In a black hole, quantum physics and gravity are forced to interact directly. Hawking radiation is the result of that interaction. It arises when the uncertainty and fluctuations of quantum fields meet the warped spacetime created by intense gravity. The fact that this interaction produces a real, physical effect tells us something crucial. Our universe cannot be fully understood by studying quantum physics and gravity in isolation. Reality is woven from both at once. This is why black holes are often called nature's laboratories. Scientists cannot create black holes in controlled experiments on Earth, but the universe creates them naturally. In doing so, it pushes physics to extremes that cannot be replicated in any laboratory. Near a black hole, gravity becomes so strong that time slows dramatically, space curves sharply, and the boundary between inside and outside becomes absolute. These conditions expose behaviors that are normally hidden. Hawking radiation is one such behavior, revealed only when nature is pushed to its limits. Black holes are laboratories, not because they are convenient, but because they are unforgiving. They do not allow approximations to hide mistakes. If a theory works only under gentle conditions, a black hole will expose its weaknesses. Hawking radiation emerged because physicists dared to apply known laws in an extreme environment and follow the consequences honestly. The result was uncomfortable, but it was revealing. One of the most important lessons Hawking radiation teaches us is about space-time itself. We often think of space and time as a stable stage on which events happen. Objects move through space. Time ticks forward independently. Hawking radiation shows that this picture is incomplete. Space-time is not just a backdrop. It participates in physical processes. The event horizon of a black hole is not a material object, yet it has physical consequences. It changes how particles behave. It affects temperature, energy, and information. This tells us that space-time has structure. It is not infinitely rigid or passive. Under extreme conditions, it can behave in ways that mimic physical systems. It can have temperature, it can have entropy, it can influence what exists and what does not. Hawking radiation suggests that space-time itself may have microscopic degrees of freedom, hidden layers that only reveal themselves when gravity becomes strong enough. This idea is deeply unsettling because it challenges the feeling that reality is solid and fixed. In everyday life, we trust our senses. Tables feel solid, the ground feels firm, time feels steady. But physics tells us that solidity is an illusion created by electromagnetic forces and quantum effects. Hawking radiation pushes this lesson further. It tells us that even space and time, which feel absolute, may be emergent rather than fundamental. They may arise from deeper rules that we do not yet fully understand. The idea that reality is not as solid as it feels is not new in physics, but Hawking radiation reinforces it in a dramatic way. Something that looks empty can produce particles. A boundary that cannot be touched can have temperature. An object that traps everything can still lose energy. These are not poetic metaphors. They are physical statements supported by theory. They suggest that what we experience as solid reality is only the surface of something deeper and more flexible. Perhaps the most inspiring aspect of Hawking radiation is how it came from simple ideas. Hawking did invent exotic new particles or propose radical new forces. He took existing concepts seriously: quantum fluctuations, event horizons, conservation of energy. He asked what happens when these ideas are combined honestly. The result shook deeply held assumptions. Black holes were once thought to be eternal. Hawking radiation showed they are not. Empty space was once thought to be nothing. Hawking radiation showed it is active. Boundaries were once thought to be passive. Hawking radiation showed they can shape reality. This is an important lesson about how science progresses. Revolutionary ideas do not always come from complicated mathematics or dramatic experiments. Sometimes they come from asking a simple question at the right place. What happens if we stop separating quantum physics and gravity? What happens if we treat empty space as real? What happens if we take horizons seriously as physical features rather than abstract lines? Hawking radiation also reminds us of humility. Our best theories are powerful, but they are not complete. The fact that Hawking radiation raises unresolved questions about information, space-time, and the ultimate laws of physics tells us that we are still exploring. The universe is not obligated to make sense according to our intuitions. It reveals itself slowly, often in ways that force us to rethink what we thought we knew. There is also a philosophical lesson here. Hawking radiation suggests that permanence is rare in the universe. Even the most extreme objects eventually change. Even the darkest places glow faintly. Even the strongest boundaries are not absolute in their consequences. Change is built into reality at every level. It may be slow, it may be subtle, but it is unavoidable. This idea connects the smallest scales of quantum physics to the largest scales of cosmology. It tells us that the fate of the universe is shaped not only by stars and galaxies, but by the quiet behavior of empty space and time. Hawking radiation is a bridge between scales, linking the microscopic and the cosmic in a single concept. Whenever an idea in physics sounds powerful or mysterious, it quickly attracts the imagination of science fiction. Hawking radiation is no exception. The thought that black holes emit energy has inspired visions of advanced civilizations tapping into that energy, using black holes as power plants, engines, or even weapons. In fiction, a black hole can become a glowing battery, endlessly supplying energy to starships or entire planets. These ideas are exciting, but they blur the line between what physics allows in principle and what reality permits in practice. To understand whether humans could ever use Hawking radiation, we need to separate imagination from physical limits. In real science, Hawking radiation is not a convenient or abundant energy source. It exists, but it is extremely weak for the kinds of black holes that actually exist in the universe. A black hole formed from a star emits such a tiny amount of Hawking radiation that it would be useless for any practical purpose. The energy output is far smaller than the energy falling into the black hole from its surroundings. Trying to harvest this radiation would be like trying to power a city using the warmth of a single snowflake drifting through a furnace. The energy problem becomes clearer when we think in everyday terms. To generate useful power, you need a strong and controllable flow of energy. The sun provides this because it is incredibly hot and massive, and it releases energy continuously through nuclear fusion. Hawking radiation does not work this way. For large black holes, the temperature is extremely low. The radiation they emit is faint and spread out. Capturing it would require equipment larger than planets, and even then the energy collected would be negligible. One might then wonder whether smaller black holes could be used instead. Smaller black holes emit much stronger Hawking radiation. In theory, a tiny black hole could be extremely hot and release enormous amounts of energy. This idea often appears in science fiction, where artificial black holes are created and harnessed as power sources. But this is where theory collides with harsh reality. Creating a small black hole is far beyond any technology we can imagine today. To form a black hole, you need to compress a huge amount of mass or energy into a very small space. The energy required to do this for even a microscopic black hole would be enormous, far greater than any energy source humans currently possess. Even if such a black hole could be created, controlling it would be another problem entirely. Tiny black holes are not just powerful, they are dangerous. A very small black hole would emit Hawking radiation intensely. This radiation would include highly energetic particles capable of destroying nearby matter. Any attempt to use such a black hole as a power source would face the problem of containment. How do you hold a black hole in place without it consuming or irradiating everything around it? Gravity cannot be turned off or shielded. The black hole would either fall through matter or drift uncontrollably. There is also the problem of stability. Small black holes evaporate quickly. The more energy they emit, the faster they lose mass. This creates a runaway process. A tiny black hole would grow hotter and more energetic as it shrinks, eventually releasing its energy in a violent final phase. Using it as a steady power source would be almost impossible. It would be like trying to run a power plant using a fire that grows more intense the more fuel it loses. Another idea sometimes mentioned is capturing Hawking radiation from naturally occurring small black holes, possibly formed in the early universe. These hypothetical objects, sometimes called primordial black holes, could in theory emit detectable amounts of radiation today. But their existence is still unconfirmed. Even if they do exist, they would be extremely rare. Finding one close enough to be useful would be extraordinarily unlikely, and approaching it safely would be a challenge far beyond current engineering. This gap between science fiction and real science highlights an important point. Just because something is possible in theory does not mean it is usable in practice. Physics allows Hawking radiation, but it also imposes strict limits on how much energy is available and how it can be accessed. These limits are not technological barriers that could be overcome with better tools. They are fundamental constraints built into the structure of the universe. That said, it would be a mistake to conclude that Hawking radiation has no practical value at all. Its value may not lie in direct use, but in understanding. Hawking radiation teaches us how energy, gravity, and quantum effects interact. This knowledge could influence future technologies in indirect ways. Many technologies we rely on today, such as semiconductors and GPS systems, emerged from abstract research that once seemed impractical. Future civilizations, far more advanced than ours, might understand space-time in ways we cannot yet imagine. They might discover ways to manipulate gravity or quantum fields with precision we do not possess. They might find ways to create stable horizons or horizon-like systems that mimic some aspects of black holes without their dangers. If such technologies ever exist, they would likely be based on principles hinted at by Hawking radiation. It is also possible that our current understanding of Hawking radiation is incomplete. A full theory of quantum gravity could reveal new aspects of how energy and information behave near horizons. These insights might open doors we cannot yet see, but even then, the direct use of Hawking radiation as an energy source would likely remain impractical for anything like human civilization. What Hawking radiation truly offers is not a power supply, but a guide. It points toward deeper laws of nature. It shows us that empty space is active, that boundaries matter, and that gravity and quantum physics are inseparable. These lessons could shape future physics in ways that lead to entirely new technologies, ones that do not resemble science fiction fantasies of black hole engines. In many ways, the idea of using Hawking radiation reflects a human tendency to focus on control and exploitation. We ask whether we can use something, whether it can serve us. Hawking radiation invites a different perspective. It invites understanding rather than use. It reminds us that some phenomena exist not to be harvested, but to be learned from. When we look at the night sky today, it feels alive. Stars shine, galaxies glow, and light fills space in every direction. It is easy to believe that the universe will always look this way, but the universe has a long memory and an even longer future. Hawking radiation plays a quiet but crucial role in shaping that future. To understand its significance, we need to imagine a time far beyond stars, far beyond galaxies, and far beyond anything familiar. In that distant era, black holes become the main characters in the story of the cosmos. The first major change in the universe's future comes when stars begin to die. Stars shine because they burn nuclear fuel. This fuel is not infinite. Over billions of years, stars exhaust the hydrogen in their cores and either fade away gently or explode dramatically. Eventually, no new stars will form. The raw material needed to make them will be used up or scattered too thinly to collapse again. This marks the end of the era of starlight, an era that has already been running for billions of years, but will not last forever. After the stars are gone, the universe enters a quieter phase. White dwarfs, neutron stars, and black holes remain as the main relics of stellar evolution. White dwarfs slowly cool and fade into darkness. Neutron stars, dense and exotic, also cool over time. Neither produces new light. Black holes, however, do something different. They do not shine like stars, but they persist. They survive mergers, collisions, and the slow expansion of the universe. As galaxies drift apart and stars vanish, black holes remain as the most massive and durable objects left. This is why black holes dominate the far future of the universe. They are not the most energetic objects, but they are the most patient. Their gravity allows them to endure long after other structures have faded. Supermassive black holes sitting at the centers of galaxies are especially long-lived. Even as galaxies themselves dissolve into isolated stars and remnants, these black holes remain intact. Over unimaginably long timescales, smaller black holes may merge into larger ones, creating even more massive and stable objects. As the universe continues to expand, distances between objects grow larger. Galaxies move beyond each other's reach. The universe becomes colder and emptier. This leads to what is often called the dark age of the universe. It is a time when there are no stars, no glowing nebulae, and no bright sources of light. Space is dominated by darkness, with only faint background radiation and isolated remnants drifting through it. In this dark age, black holes become the last light sources, though their light is nothing like the starlight we know today. Hawking radiation is incredibly faint, but in a universe that has grown cold and quiet enough, it becomes significant. When everything else has gone dark, even a whisper becomes noticeable. Black holes, once seen as perfect absorbers of light, become the final contributors of energy to the universe. This is one of the most poetic aspects of Hawking radiation. Black holes begin as objects defined by darkness. They end their lives as the last sources of light. Their glow is not bright or warm. It does not illuminate galaxies or cast shadows, but it exists. It represents the final release of energy stored over cosmic history. In a universe with no stars, no planets, and no life, black holes quietly radiate their remaining mass back into space. This process unfolds over timescales so long that ordinary numbers lose meaning. Trillions upon trillions of years pass. Black holes slowly shrink. Their radiation becomes slightly stronger as they lose mass. One by one, they disappear. Stellar mass black holes evaporate first. Supermassive black holes, containing millions or billions of solar masses, last the longest. They are the final giants of the cosmos. As the last black holes evaporate, the universe enters its final phase. There are no massive objects left to curve space strongly. Matter is spread thinly and evenly. Only low-energy particles and radiation remain. The universe approaches a state of maximum entropy, where energy differences are minimized and no useful work can be done. This is often referred to as the heat death of the universe. In this final state, change becomes extremely slow. Without stars or black holes, there are no dramatic events, no explosions, no creation of new structures. Time still passes, but nothing of interest happens on any meaningful scale. The universe becomes a place of quiet, nearly eternal stillness. Hawking radiation is central to this picture because it ensures that black holes do not remain as permanent structures. Without it, black holes would survive forever, locking away mass and energy indefinitely. With Hawking radiation, even black holes eventually return their energy to the universe. Nothing remains isolated forever. Everything participates in the long, slow flow toward equilibrium. This view of the universe's fate can feel bleak, but it is also strangely elegant. It suggests that the universe has a kind of closure. Processes begin, evolve, and end. Even the most extreme objects are temporary. There is no eternal hoarding of energy. The cosmos tends toward balance, not permanence. Hawking radiation also connects the far future of the universe to its deepest laws. The same quantum fluctuations that shape empty space today will determine how the universe fades tomorrow. The same principles that govern tiny particles also govern the fate of galaxies and black holes. This unity is one of the most beautiful aspects of physics. It is worth remembering that this vision of the future is based on our best current understanding. New discoveries could change the details. Dark energy, unknown particles, or new physics could alter the long-term evolution of the universe. But within our current framework, Hawking radiation plays a decisive role. It ensures that the universe does not freeze into a static state, dominated by eternal black holes. Instead, it continues to evolve, even in its darkest era. Some ideas in science do more than solve a problem. They change the direction of thinking itself. Hawking radiation is one of those ideas. Before it was proposed, black holes were seen as simple, final objects. They swallowed everything and gave nothing back. After Hawking radiation, black holes became dynamic systems, capable of change, temperature, and evolution. This single insight reshaped black hole physics and rippled outward into cosmology, quantum theory, and our broader understanding of reality. Before Hawking's work, black hole physics was almost settled. Black holes were described by only a few properties: mass, charge, and spin. This simplicity was elegant, but it also made black holes feel disconnected from the rest of physics. They were exceptions rather than participants. They did not behave like ordinary physical systems. They did not radiate. They did not cool. They did not age. Hawking radiation changed that picture completely. It showed that black holes obey the same basic laws as other systems. They have temperature. They emit radiation. They evolve over time. This brought black holes back into the family of physical objects, governed by thermodynamics. This shift had immediate consequences. If black holes have temperature, they must also have entropy. Entropy measures how many internal configurations a system can have, or how much information is hidden within it. The idea that black holes have entropy was revolutionary. It suggested that the surface area of a black hole's event horizon is related to the amount of information it contains. This connection between geometry and information was unexpected and profound. It hinted that space-time itself might be built from informational building blocks. The influence of Hawking radiation quickly spread beyond black hole physics. It became a central piece of modern cosmology, the study of the universe as a whole. Black holes are not rare curiosities. They're common features of galaxies. Understanding how they behave affects our understanding of galaxy evolution, the distribution of matter, and the long-term fate of the universe. Hawking radiation ensured that black holes are not permanent sinks of matter and energy. This helped clarify how the universe evolves over extremely long timescales. In cosmology, Hawking radiation also reinforced the idea that the universe is governed by thermodynamic principles. The universe has a temperature. It has entropy. It evolves toward equilibrium. These ideas might seem abstract, but they shape how scientists think about cosmic history. Hawking radiation connected the smallest quantum fluctuations to the largest cosmic structures, showing that the same laws operate at all scales. This is why Hawking radiation appears in textbooks today. It is not treated as a speculative curiosity. It is presented as a fundamental result that students must understand to grasp modern physics. It appears in courses on quantum field theory, general relativity, cosmology, and black hole physics. Its inclusion reflects the confidence scientists have in the idea, even though direct experimental confirmation remains elusive. The reasoning behind Hawking radiation is sound, and its implications are too important to ignore. Textbooks include Hawking radiation because it teaches more than a specific result. It teaches a way of thinking. It shows how combining established theories in new contexts can lead to unexpected discoveries. Students learn that physics is not just about applying formulas, but about understanding how concepts interact. Hawking radiation is a case study in intellectual courage and careful reasoning. One of the most enduring lessons of Hawking radiation is that questioning the impossible can lead to progress. For decades, the idea that black holes could radiate seemed absurd. It contradicted the very definition of a black hole. Most physicists did not seriously consider it because it felt obviously wrong. Hawking himself initially expected to prove that black holes do not radiate. He followed the math to confirm the existing belief. Instead, the math led him somewhere unexpected. This is an important point. Hawking did not start by rejecting established ideas. He respected them. He trusted Einstein's theory of gravity and the principles of quantum mechanics. But he also trusted logic. When the logical consequences of combining these theories pointed toward radiation, he accepted the result, even though it was uncomfortable. This willingness to accept strange conclusions is one of the driving forces of scientific progress. The legacy of Hawking radiation is not limited to its specific predictions. It inspired entire fields of research. The black hole information paradox, sparked by Hawking radiation, has driven decades of work in theoretical physics. It has led to new ideas about holography, quantum entanglement, and the nature of space-time. These ideas have applications far beyond black holes, influencing how physicists think about the fabric of reality itself. Hawking radiation also changed how scientists view boundaries. Event horizons were once seen as simple dividing lines. After Hawking, they became active regions with physical properties. This shift in perspective has influenced research on other horizons as well, such as cosmological horizons associated with the expansion of the universe. The idea that horizons have temperature and entropy has become a general principle, not a special case. Another part of Hawking's legacy is cultural. His work captured the public imagination and brought deep questions about the universe into popular discussion. Hawking radiation became a symbol of how abstract thinking can lead to profound insights. It showed that even the darkest corners of the universe are governed by elegant rules. This helped bridge the gap between professional physics and public curiosity. Perhaps the most important legacy of Hawking radiation is humility. It reminds scientists that even widely accepted ideas can be incomplete. Black holes were thought to be fully understood. They were not. Empty space was thought to be passive. It is not. Boundaries were thought to be uninteresting. They are crucial. Hawking radiation teaches us that nature often hides its deepest secrets behind assumptions we no longer question. At first glance, Hawking radiation seems distant from everyday life. It happens near black holes, objects so far away and so extreme that they feel disconnected from human experience. It unfolds over timescales that stretch far beyond the lifetime of stars, let alone civilizations. It involves particles and equations most people never encounter. And yet, understanding Hawking radiation matters, not because it will change what we do tomorrow, but because it shapes how we understand our place in the universe. It tells us something fundamental about reality, about time, about limits, and about the power of human curiosity. Understanding the universe has always been part of being human. Long before science existed, people looked at the sky and asked questions. What are those lights? Where did they come from? What lies beyond them? These questions were not practical. They did not help build houses or grow food, but they mattered because they connected people to something larger than themselves. Hawking radiation belongs to this tradition. It is not about usefulness in a narrow sense. It is about meaning. It is about understanding the rules that govern everything, from the smallest particles to the largest structures in existence. There is a tension at the heart of this story. On one side is the cosmic scale. Black holes, galaxies, and the slow death of the universe operate on scales that dwarf human life. On the other side is human curiosity, a fragile, short-lived species asking questions about things it will never touch or see directly. This contrast can feel overwhelming, even discouraging, but it is also deeply inspiring. The fact that humans can understand something as strange as Hawking radiation at all is remarkable. It shows that curiosity is not limited by size or distance. Ideas can travel farther than bodies ever could. Hawking radiation itself is a perfect example of how small ideas can change everything. The idea that empty space is not truly empty. The idea that time slows near gravity. The idea that boundaries matter. None of these ideas sound dramatic on their own, but when they are combined, they overturn centuries of assumptions. They turn black holes from eternal prisons into temporary structures. They reveal that even darkness has a faint glow. They show that the universe is not static, but evolving at every level. This is an important lesson beyond physics. Progress does not always come from big, obvious breakthroughs. It often comes from quietly re-examining things we think we already understand. Hawking did not invent black holes. He did not invent quantum physics. He asked what happens when we stop treating them as separate. That simple question reshaped science. It reminds us that curiosity is not about having all the answers. It is about being willing to ask better questions. There is also a deeper, emotional meaning to Hawking radiation. Black holes are often symbols of fear. They represent the unknown, the inescapable, the end. Hawking radiation softens that image. It does not make black holes harmless, but it makes them part of a larger story. They are not eternal monsters lurking at the edges of the universe. They are temporary features in a universe that changes slowly, but relentlessly. Even the most extreme objects eventually fade. This perspective encourages wonder rather than fear. The universe is not out to trap or punish. It follows deep, consistent rules. Those rules can produce strange and sometimes unsettling phenomena, but they are also elegant and beautiful. Hawking radiation shows that the universe is subtle. It does not announce its secrets loudly. It reveals them through quiet processes that require patience and imagination to understand. There is also something profoundly human in this story. Stephen Hawking studied the fate of black holes while facing the limits of his own body. He explored cosmic endings while living with a condition that forced him to confront time personally. Yet his work was not driven by despair. It was driven by curiosity and a belief that understanding matters. Hawking radiation stands as a testament to the idea that the mind can remain free even when the body is constrained. In a broader sense, Hawking radiation reminds us that permanence is rare. Everything changes, even things that seem unchangeable. This is not a cause for sadness. It is a reminder to value the present and to appreciate the fleeting nature of existence. Stars shine for a time, civilizations rise and fall, even black holes evaporate. Change is not a failure of the universe, it is one of its defining features. Understanding this can bring a sense of calm. The universe is not static, but it is not chaotic either. It follows patterns that can be understood. Hawking radiation fits into those patterns. It shows that the universe has a kind of balance. Energy is not trapped forever. Information, in some form, may not be lost. The cosmos evolves towards states of greater simplicity and quiet. As this story comes to an end, there is no dramatic conclusion, no explosion, no final answer that resolves every mystery. That is fitting. Hawking radiation itself is quiet, subtle, and slow. It does not demand attention. It invites reflection. It encourages us to think beyond immediate concerns and imagine the universe on its own terms. The real value of Hawking radiation is not in what it tells us about black holes, but in what it tells us about thinking. It shows that reality can be understood, even when it defies intuition. It shows that asking questions about the far future can deepen our appreciation of the present. It shows that curiosity is a powerful force, capable of bridging the gap between human experience and cosmic scale. As you step away from this topic, there is no need to feel small or insignificant. The universe may be vast, but understanding it is a human achievement. Hawking radiation exists whether we know about it or not, but knowing about it changes us. It expands our sense of what is possible. It connects us to a universe that is richer and more mysterious than it appears. In the end, Hawking radiation leaves us not with fear, but with wonder. A quiet wonder at the fact that even in darkness, there is light. Even in emptiness, there is activity. And even in the most extreme corners of the cosmos, the universe follows rules that the human mind, patient and curious, can begin to understand.